Hey, that was easy. Hello there. My name is Aid. I lead the engineering teams for Gilt.com across New York and Dublin, and it's on behalf of those guys that I'm presenting here today, also with the great Derek Childs. So effectively, we got together and we had this idea, why don't we talk about the things that Gilt has done specifically around moving to a microservices architecture on AWS over the last 3 or 4 years. And there's a lot of things that in Gilt that we've learned ourselves, you know, of how we've kind of come across and answered some of the problems. So, and then Derek is going to talk then more about, like, from the other customers that he works with, the general patterns that he's seen in terms of adopting microservices in the cloud. So, I'll start talking about Gilt and Gilt's journey. Because this is America, a lot of you guys may actually know what Gilt is. But for me, it's really important to kind of get a feeling for, like, you know, what is Gilt, and even, like, why does Gilt need a tech team? So the way I think about it is, so Gilt, its concept is luxury brands given to you at a discounted price, okay? And the way the business works is, so we've got these great merchants, and what they do is they work with our designers and brands across the world to select and curate really, really great product and bring that to our customers, okay? So this is one of our stylists. And then when we get the products arrive to us to sell. You know, and what we discovered as part of growing this business is when we get these beautiful bags and dresses and, you know, whatever shoes, whatever these things are, it turns out that the vendors, the brands themselves, may not actually have very good photographs. And we want to make this product look absolutely great, okay? So at Gilt, we actually have our own photo studios and our own creative studios. And what we do is we shoot that product and we make it look fabulous for our site, okay? I love working in a real business. So this is our warehouse in Kentucky. We receive physical product. We put it on our shelves, and then we turn it around, and then we ship it out, okay? It's really, really nice to work for a company that deals in real things. Now, why am I telling you all of this? The reason I'm telling you all of this is because the Gilt business model is a very, very unique business model, okay? And it turns out there is no off-the-shelf software that you can buy that can run a business like Gilt. And so what we've done since inception is we've actually built a huge amount of that software ourselves, okay? So the software that we use to curate the brands and actually get the products together, the software that we use in our studios, you know, to manage all of our photo shoots, the software that we use in parts of our warehouse, that's all written by our engineering team. One of the big things then about Gilt then is that the sales, it's all about the rush. The sales go live every day at noon, and there's a really great thing that happens here. We send out at approximately 11:45 every day EST. We send out approximately 5.5 million emails. Okay, and these emails go out to our members, and they say, "Hey, here's the products and the sales that we have today for you." Okay. And that's amazing. So we send 5.5 million personalized emails and push notifications. And then our customers stampede the site. It's our very own self-denial of service attack, okay, from our own marketing department, okay? This is our customer base, okay? It's really fun to think of our customers, you know, as a herd of steaming wildebeest. In fact, from a technical perspective, they don't actually look like this. What they look like is this, okay? This is the reason why I am thrilled to work at Gilt. This is a profile of the traffic on any given day. And what you see around just before 16 there, which is noon EST, what you see is this gentle rise. That's from the second that we start sending out our notifications and our emails, okay? And then you can see the pulse load, right? Once the sales go live at noon, that's the rush, okay? Everything that we build, apart from all the stuff that we do to build the business process and to build, you know, everything that runs the back office of the business, everything we do in the front end has to scale to this, okay? It has to be resilient to that spike, okay? And that's one of the really, really great things about working at Gilt. There's another interesting thing here, which which I learned when I joined, is that failure here is not uniform, or rather the cost of failure is not uniform. Okay? The amount of money we bring on any one given day happens in those 2 or 3 hours after the spike. That's when we are earning dollars, right? If the site goes down or the apps go down at that moment in time, that is expensive, okay? Yet for the rest of the day, as you can see, the cost of failure is actually much, much lighter, okay? So it affects how we think about things. So we need to be solid for this noon rush every day. So let's talk about then, like, how did it start? And how did we get from what was originally a super monolith to a highly distributed microservice architecture, okay? So here was our architecture in 2007, and it was it's great. This is like the Rails to riches story, okay? A bunch of guys get together, right? They program Ruby on Rails, okay? And so their architecture diagram is really like a big box and then a cylinder, right? And that's it, okay? And that's actually great. I mean, I've programmed with Ruby on Rails over the last couple of years, and it turns out actually Ruby on Rails is brilliant. I mean, it's a fantastic language, it's a great framework, it's absolutely fabulous. The only problem for us is that it didn't scale, okay? Now, there'll be people, Ruby lovers who will be like, oh, but look at me, no, you can do it. And we're like, we tried. Like, we tried very, very hard. We had the best Ruby engineers on the planet working with us. And really, the problem, in a sense, wasn't Ruby, it wasn't Rails. The problem was our customers, right? There was one day when we had Christian Louboutin, which is a brand of footwear. And that day was one of those days when your site goes viral. And that was one of the first days that the site went down, right? Nicely, because the site went down, they kept on hitting the site so that when it came back up, there was even more pent-up demand, right, which was great. So, when you're trying to scale something, you've got a couple of things that you're going to try and do. We added memcache to the right to kind of speed things up. We also have a separate job system that takes a lot of our offline processing, but this was roughly our architecture. So we realized it didn't scale. Okay, so what did we do? We adopted a technology called Java, J-A-V-A technology. And effectively, the way we did it was actually, I think, kind of interesting. So what we did was we said, there's really two kinds of traffic for Gilt. There's the traffic that's internal, right, from the people who are working for Gilt and setting up sales and actually, the business process, right? We left those people over on the left of the chart. We left those on the Ruby on Rails app, and that's fantastic because Ruby allows us to build the tooling very quickly for those guys, okay? But for the massive amount of bulk load on the site, we did that through a bunch of Java services. And I'll just briefly explain the architecture here. To the bottom right of the chart, you can see some big old services for some classic kind of business entities in an e-commerce company. You've got user service, product service, cart service. We had a number of these really, really big services. Then north of that, you've got this layer for content page assembly. And you see we have a number of services there, PageGen for generating pages, a city service. Effectively, what we did was we separated our business, our technology stack by the different businesses that Gilt was running at the time. Okay, so we have classic siloed business lines and siloed business architecture. Okay, and then the front end here that was delivering all the web pages was done using JSPs. Okay, so this was actually, in a sense, okay, it's fine. It's fine until it isn't. Okay. The services that we were using, they were little mini monoliths of their own, okay? Our product service loads all of the products and sales into memory so that when the noon rush comes, we serve everything from memory. That's fantastic. The only problem now is that it takes 20 minutes to start the service up, okay? It's a great big behemoth, okay? What else is there? We had these teams that were focused solely on business lines. We had effectively this monolithic, huge Java application. We called it Swift. And that was over two parts. First, Swift, the front end that drove the pages, and then PageGen that did the content assembly. Okay? And that's like two great big repos and 100 engineers trying desperately to commit code to those repos. Okay? Incredibly hard. And as an engineer, it's like, so 1 week you're doing a feature, you implement the feature, and it goes into this really, really long queue to get QA'd, and then it goes through the QA and it fails, and then it comes back to you 3 or 4 weeks later. You're moving on something else right now, but you've got to go back in time and try and figure that stuff out. Very, very hard. So what we found was the architecture was very, very much impairing us. One of the other things we found then as well was because we were all sneaking stuff desperately in, we were all breaking our own rules. And so we started doing things like sending little lines straight to the database to get a little hack in really quick, okay? And effectively what we ended up with was something of a mess. Something of a mess that could fail on any given day and bring down noon, right? And that's a terrible position to be when effectively, the business relies on us to keep the site up and we're down at noon. Okay, so had this moment, by the way, here where we basically said, there was a day I needed one piece of information. I needed the shipping message, or rather the marketing message on any given day for a given user. And it was like, hey, it's not like 20% off your shipping today or free shipping today, whatever. I want a service. I've got a user information, and I want to find out what their message should be. Okay. And I looked at the architecture and I looked at the code, and I discovered that if I wanted that one piece of information, the marketing message of the day, I'd have to go deep into that page gen service and get kilobytes of JSON data that describe the front homepage of our site and scrape right into that just to get that one sentence, right? There was something wrong. So at the time, I was chatting with our CTO back then, the great Mike Brzyk, and I was saying, I think what we need is a little service, right? I think we need like a service that just has one endpoint, okay? The endpoint is going to do this thing, give you the marketing message of the day. And we were chatting, and what we were talking about sounded so completely crazy, right? Like, we're going to set up a whole Java virtual machine on 4 instances, or we're going to have it just serve that one little endpoint. It was absolutely destined to failure, so we did it, okay? And that actually was our first microservice, and it was great, actually. It was really, really exciting. So the big thing, though, around that time was how do we arrange our teams, away from this big monolith, trying desperately to get little features for the businesses in. How can we organize our teams, and our software so that it's really easy to get stuff to production, and that we can really have a big positive impact on the business? So enter microservices, okay? 2015, this is a very, very high-level view of our architecture, and a number of things have happened here, okay? Some of the old players are still there. The big old database, it's still there, right? Some of those big old services still there, although a little smaller or different shaped. But what you'll notice is a forest of services, right? Some of them are for our admin tooling, and some of them are for our site itself, okay? And these are the microservices tier that many of our apps use. One of the other things we did as well, breaking up the monolith north of the picture, we actually broke our big monolithic web application into multiple applications, right? And again, this sounds kind of crazy, but effectively, when you go to Gilt.com and you move from different pages on the site, you're actually moving and being served by entirely different apps, okay? And that's actually turns out a great thing, because if you've got a team that's working desperately on a feature for the product detail page, it doesn't affect the guys who are doing search or loyalty or personalization, and they can deploy software in their own time, and they can get their code out to production. So, so how did we get here? It's interesting. There was never any moment when a bunch of us got into a room and got pens and wrote over all the walls and said, "Here's the architecture," right? Effectively, what happened was we just started saying, let's build what we need. Let's actually get teams together. Let's give them a problem to solve. And then let's let them build whatever services they need to solve those problems, okay? So there's a number of things that socially were really important in terms of our culture that allowed the architecture to evolve, okay? So a couple of key things here. One of the things that we do at Gilt is voluntary adoption. If you've got a great idea, a great tool, a great new piece of technology, that's brilliant, okay? We never force that technology on any of our engineers, right? If it's really as great as you say it is, then people are going to adopt it, okay? And then it's going to be really great, okay? So it turns out that principle has been really, really important in how we eventually evolved our entire tooling set. Okay, I'll move on for the importance of time. So here's the number of services and our service growth over those periods. This is really, really interesting. You see this really great moment of inflection there, where we're growing, 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 and then sometime, which is actually dated February 2012, we discovered that we'd been toying with this Scala programming language for too long. We were officially a Scala shop, okay? And with that adoption of the new language and the adoption of a lot of the techniques that we built around deploying to production, we found that it was really, really easy to create services, and as a result, we created tons of services, okay? So we're actually now, we've leveled off now. We're probably in the region of about 300 different services across the business. So what are the services doing? I mean, the services are capturing so many different parts of our business. They're there for our recommendation systems, our email systems, our notification systems, to do with calculating shipping delivery windows. Anything that we think is a nugget of really useful, important business logic, we try and get into a service. Now, in more concrete terms, what's the kind of the architectural choices that we use when writing a service? So the way I think about it here is largely, we're using the JVM. Typically, you've got some kind of framework, framework for hoisting up some JSON endpoints, because effectively all of our services are holding JSON over HTTP. You drop in your code into that framework, and then there's a couple of other kind of pluggable things. You need some monitoring, you need some logging. One of the big things that's really important for microservices is that a service typically has its own data store, right? And it completely owns its own data store. And that's a really, really important thing you should think about. If you're going to do microservices and say, yeah, I've got 100 services and they're all pointing to the same database, that's a bad idea. It's a bad idea because one schema change on that database can break 99 services, right? So you really want to make sure that your service fully owns its own data. So then the technology choices, like in a world of voluntary adoption and total freedom for the developers to pick whatever they want, we've kind of ended up arriving on the following. We've got a couple of different options. We have our own internal, very, very lightweight service framework at Gilt. We also use Play Framework now. Play Framework is actually built for web applications and rendering HTML. It turns out it's really, really good for writing services. Really, really fabulous. Monitoring-wise, we use New Relic extensively. It's a fantastic tool. We also have an internal tool called Cave. Cave allows us to do some really, really interesting things. Our services emit events. We listen for those events for patterns and time series. We also listen for the absence of events. So we can create an alert around the idea of, if there are no orders shipped to the United States in the last hour, raise an alarm, right? And that's a really great way to think about things. Like whatever about the technical things that could be going wrong. If you look for the business things that should always be true, when they're not true, there's something broken, right? That's what Cave allows us to do. We open sourced that recently. It's on cavellc.io. For logging purposes, we use a mixture of Log4j, a number of logging tools. We also use a lot of CloudWatch extensively now. Programming languages, Scala, Java, and JavaScript, and also we're beginning to use Node as well in our services. So you think, are the services, are they really microservices? Well, the lines of code per service, as you can see here, it's a logarithmic scale. So most of our services have approximately 2 to the 11, which is 2024 lines of code. That's actually really nice, because you can drop into a service and pretty quickly figure out what the hell the service is doing, because there's not that much code in there. In terms of source files per service, right, we've got 2 to the 5, okay? That's 32. That's really nice as well, okay? So any particular service doesn't really have that much in its repo, okay? One of the big things that people have asked me in the past is, how do you do discovery, right? And this is really, really important. Discovery is enormously simple. Now, people will tell you discovery is enormously hard so that they can sell you something to solve the problem of service discovery, right? In fact, right, we found that actually it's very, very simple. So first thing is discovery is a client needs to get to a service. How's it going to do it? Well, it's got a name of a service. I need to look up that URL, right? So what we do is we use Zookeeper as a highly available store. We say, give me the configuration. We get the configuration back with the URL. And then we make a RESTful call on the service. Now, our services are always, our services are always fronted by a load balancer. The load balancer that we've used in the past, we call it Zeus, okay? But through the miracle of marketing and acquisitions and business, Zeus has gone through a number of incarnations. It became Stingray, then SteelApp, and is now called Brocad, okay? We find this to be a great tool. We use it extensively. And effectively what it does is it takes over a huge amount of the highly availability and fault tolerance and scalability that we need for all of our services. Everything just goes through that middleman. And then it's just a RESTful call on the service to go forward. Now, so we used to be on bare metal. We used to run all of our services and all of our infrastructure across 2 data centers in the United States. And this year, we made the big move. This year, we went to Vapor. We took it all and we moved it to the cloud. And we were able to do so in a period of approximately 3 months. And that was after about 6 to 9 months of very intensive work. But this was actually an enormous achievement for us. And we got over the fear around, hey, you've got these services, they're on bare metal, they're not going to be on bare metal anymore. How are we going to deal with that? It turns out that the performance that we've had on Amazon has been absolutely fabulous. So how did we do it? So you take the existing data centers. Effectively, what we did then is we created a legacy VPC, a VPC, we call it legacy VPC in Amazon. And then we connected the two with a dual 10 gigabit direct connect line. Okay? There was a talk earlier on, a fabulous talk on direct connect, really, really great product. And that had a 2 millisecond latency between our data center and our VPC. Okay? So then what you do is, the stuff that you were originally deploying to the data center, we said, well, let's just move those over to Amazon machines now that are being deployed in the VPC. This is called a lift and shift, right? Some people call this an anti-pattern, right? I call it the easiest way to get from A to B, okay? So we just moved the stuff over. So once we had done that, though, we then created sub-accounts for the various kind of large systems or teams in our company. Like a common account, mobile, personalization, admin, data. And the idea now is that if you as a team want to do something really, really cool with DynamoDB or any of the other big tools, or you want to do a huge amount of elasticity work, you begin to move your services into these accounts. Okay? So we've got this very, very nice hybrid model of a kind of a static lift and shift move, which got us out of our data center. But then, as our engineers now move into a DevOps model, they can have full freedom to play in the team accounts. Just some of the things that you realize, some of the questions like, oh my God, how are we going to do this? Should we have many services per EC2 instance? Right? We looked at this and we said no. Okay? We said no because what we have found is co-locating or having multiple services on the same box for us is a really bad idea. The number of noons we've lost because one rogue service took down 10 other services that were on the same box, right? We couldn't have it, okay? So we actually said, let's deploy a single service instance per EC2 instance. That's good. The other thing that we've done is a lot of our servers are now deployed using Docker, right? Docker is great in terms of giving us repeatable deploys. We have a clear-cut, immutable definition of what the service is, and that's fantastic. What we've actually moved towards saying now is the container gives us immutable deploys, but the instance, or the EC2 instance, gives us a sense of mutability that we need. Okay. And then in this new architecture, how does service discovery work? Well, it actually turns out to be easy. We're still using Zookeeper for the original lookup. We get the configuration information. And then we've got a classic ELB load balancer that we're hitting off to our services. Okay? So it's the same model. It's the same pattern. It's very, very easy. And again, the load balancers, ELB, gives us everything we need in terms of high availability, fault tolerance, and scalability. So let's think the number of instances per service. When we deploy a service, we want to deploy it so that it's highly available. So what we tend to do is deploy either 3 or, as you can see here, 3 or 4 instances of any given service. Okay? This is just to make sure that we have enough instances running that if we lost 1 or 2, we'd be fine. Okay? The instance size. The instance size is very, very interesting. Because we're doing 1 JVM per instance, this means then that the vast majority of our instances are T2 micro. We also have a bunch of smalls and mediums. And then for some of the bigger behemoths, then we have some really large instances here. I like this chart because basically it means we're living the dream. We've actually got lots and lots of small services running on lots and lots of very inexpensive hardware. And that for us is a real win, okay? So it's interesting to think then, I guess this is just the entire evolution in one slide where we can say, yeah, okay, we started off as a monolith. We grew into more and more services, right? But they were still big, chunky services. And for us, the point of liberation was when we broke it all apart into lots and lots of small services. And then, of course, this year, moving to the cloud. So things that are important. So we love microservices. Effectively, having microservices has allowed us to really remove the dependencies between teams. People can just get stuff done, right? We deploy all day now, throughout the day. We deploy throughout noon. What was once the kind of the lockdown period, you must not deploy anything. We feel great about deploying there, okay? When a service goes down, it'll go down, and it won't take down the entire site. It's fine. We'll get it back up again, okay? We run lots of initiatives in parallel. Use of Docker and our general culture allows us to say, use whatever tech or language you like to build your services. We don't really mind, as long as we can get them running in the cloud, okay? So lots of great things there. I think as well, one of the things about also loving the cloud is there has been this great shift for us as teams. It allows us to do DevOps. DevOps in a real and meaningful way, all right? What we find now is our engineers get to choose the instances they run on, the databases they use, the queuing systems they use, and our engineers are quite happy to have that level of control. It's also, as well, an exceptionally low barrier of entry. To try out any new database or any new tool, we find that it's enormously good, okay? There's loads of other great benefits there. One of the other ones, though, that I just want to highlight there is cost visibility. We actually have the ability now to know how much something costs. Last week, one of my engineers in Dublin reduced the cost of Gilt.com's cart by half. Okay, and that's amazing. Now, if we didn't have that visibility on cost, he would never have known that the service was costing this much per month, right? But having that loop back to kind of say, hey, this is how much these servers are costing. And he goes, yeah, do you know what? We don't need that. We don't need that. We can scale that down. And all of a sudden, then you're actually saving money. It's fantastic. So we really, really like that. Okay, yeah, so a rollicking good time. Let's hand it over to you, Derek. And thank you very much.
All right, thanks, Aid, and hello, everyone. We appreciate your time in the famous pre-happy hour slot here on Thursday. And so, in the second half of the session today, what I'd like to do is shift from Gilt story, which is a great story from monolithic to microservices, from physical data centers to the AWS cloud, and talk more about general emergent patterns and challenges that we're seeing in AWS when we talk to Gilt and other companies that are making this journey. I think many of you that are listening and watching are either considering making a move from a traditional monolithic architecture to a microservices architecture, or possibly already committed and already on the way. And so we'd like to leave you with some things that you can take away. So before I jump into those patterns, I think it's interesting to take a step back and think about monolithic traditional architectures and microservice architectures as really a continuum, right? And so it's really going to be a journey from one side of this slide to the other. There's advantages to being in a monolithic architecture, right? It's simpler to make deployments. Your refactoring inside of an IDE is actually pretty straightforward because you've got all the code loaded in one place. You can make a couple clicks. But there are some good advantages to microservices as well. And so what we want to do here when we think about these patterns is think about minimizing the disadvantages and really playing to the strengths of the microservices model. So I'd like to walk through 6 of these challenges. This is not an exhaustive list, of course, but this is something that we've seen as we've talked to Gilt and our other customers. So I'll jump right in. So the first challenge, the first set of patterns here is around organization. And so at the high level, microservices is really an organizational or a cultural shift inside your company. And so when you start to think about moving towards microservices, many of us will be organized in a pattern that looks like this, where we have teams of really smart people that know how to do great things with technology. And so we've in this slide, we have a UI team, we have an application logic team, we have a DBA team. And what we see, and this is Conway's law, if some of you are familiar with this, what we see is that our application architecture tends to mirror our org chart. As we move forward into the microservices world, we really want to think about organizing on business responsibilities, right? What am I obligated to provide to other services or back to the business? And we're gonna range our teams around one service or around a small number of services. So this is important to think about at the beginning of the journey. And this may be a bit of a change in your organization chart, but it's really critical to have these teams feeling like they have the ultimate responsibility for these services. And so that means that you wind up with a team, and this really plays into the DevOps model very well, that sort of soup to nuts owns the service and owns the delivery of that service. They're going to own requirements gathering. They're going to pick the technology that is the best suited for the service that they need to build, the technology that they're most comfortable with. They're going to develop it. They're going to make sure it meets the quality bar. They're going to take care of deployments, often many deployments in a day, and then they're going to support it. And that means that there's no more wall to throw code over or throw deployments over. There's nobody on the other side of the wall, right? And so you've really got to own it from beginning to end. And so as we start building these teams and building these small services and sort of peeling the onion and pulling services out of our monolithic artifacts, we're going to find ourselves with dozens and potentially hundreds of microservices. And that means that we're going to be members of a community. So as service owners, we're going to be both consumers and providers of services in this community. In any community, it's important to be a good citizen. So we want to make sure that our teams are thinking about good citizenship in this new area. And so if we think about the service consumer side, which most services are going to be consumers, a good citizen means that you're going to design for failure. Right? Werner likes to say everything fails all of the time. Right? We hope that that's not literally true for our services. But it's a great mindset to take when you think about consuming services from somebody else inside your organization. So what's going to happen when you're making a service call and it times out? What happens if it's just taking a long time, if it's tar pitting you? What happens if you get an HTTP 429 that's saying, hey, slow down, you're being throttled? So you need to think about that with every service call and really think about how you can degrade gracefully. Can you continue to provide some partial service while you're having trouble talking to those other services? So expect to be throttled. Build retry logic into your client service calls. You should use exponential backoff. For example, the AWS SDKs do that by default. They're going to roughly double the amount of time that they wait in between each service call if the service call is failing. So we can give that service that's in trouble a chance to breathe and recover. And caching becomes very important in this model, and we're going to talk a little bit more about that. Caching, of course, important across the board in information technology, but as a service client, it becomes especially important. So if we think about the other side of this transaction, the service provider, being a good citizen starts with publishing your metrics. Right? Once you're on the hook for providing a service that probably multiple other services depend on, they're going to be looking for you to be able to provide things like what's the throughput that you're currently seeing, what's the error rate that you're currently seeing, what's the latency that you're currently seeing. Those are all critical metrics. And if somebody thinks that something's going on, they need to be able to go and find at least those three metrics. So think about the externally relevant metrics that your service is providing to other people and make sure that those are publicly available. The next thing is to protect yourself. So you're going to want to build throttling into your API. If you have a misbehaving client that's trying to basically do an accidental denial of service attack, you want to be able to stop them before they can take you down and cause degradation for other services. So build throttling into your API. You want to keep your implementation details private. So again, once you have dozens and hundreds of microservices in this ecosystem, if you leak your implementation details, people are going to start depending on them. And then you're going to be stuck with your implementation. So just make sure that you have a very clear service boundary. Hide your implementation details behind your API. Very important. And backwards compatibility becomes very important. Backwards compatibility, when you have a few clients, you can ask them to take an incompatible API change every once in a while. Maybe not a big deal. They might grumble about it a little bit. But you can imagine 100 services trying to make a couple of backwards incompatible changes a year, and you're going to have chaos. And so being a good service provider in this case means make forwards compatible changes, right? Add new HTTP or API methods to your service. Don't delete methods because people are going to be depending on them. Don't change the functionality. Think about adding them. Or use API versioning, which will make it easy for people to take new versions and other people can stay on the old versions. And so I'd be remiss talking about being a good service provider if I didn't mention Amazon API Gateway. So certainly you can roll your own throttling using things like Nginx and Apache HTTPD. You can roll your own caching using Elasticache, or you can build your own Redis or Memcached cluster. You can do your own monitoring. There's lots of great monitoring software out there. And you can think about versioning and authentication. Amazon API Gateway attempts to put all of those together into one package for you. So certainly suggest that you think about using API Gateway if it makes sense for your services as you start to build them out. So next, let's move on to discovery. This is something that we hear from customers as a concern as they start to build out their service architecture. How am I going to find 100 different services in this environment, right? And it turns out that it's actually usually pretty straightforward. And so the simple way to think about this is to use DNS, right? Have a well agreed upon convention for how you're going to name your services. Inject the environment that you're going to be running your service in at runtime. And since your service knows the name of the environment that it's in, and it knows the name of the service that it needs to hit, it can easily go and find typically an Elastic Load Balancer, but the DNS name that's going to provide that service. Now, there are a few issues with this. One of them is your clients might not be respecting TTL, and so if you want to make a lot of changes, they're going to be using cached DNS. And it's a pretty bare bones model. So if the simple model is not working for you, you can think about making a dynamic service registry. There's plenty of great options out there that can handle dynamic service registry. And the nice thing about those is they're going to give you additional functionality besides just where's my service. They're going to give you things like configuration management, health checks, lots of other stuff. So if the simple model looks like it's not going to work, you can take a look at some of those other options. So moving right along, the third challenge and set of patterns that we see is around data management. And so Aid talked about this in the beginning of the session here, but the monolithic world, we really are used to this pattern of a big monolithic, typically expensive, centralized database and lots of applications that are depending on that database. But there's some challenges with this model. So one of them, as Aid mentioned, is schema changes can become very difficult. If you have lots of service teams that are depending on the same schema, it could take months, potentially a number of months, to get everybody to agree and finally push that schema change out into production. It means that you're typically going to wind up locked into a single technology vendor, for better or worse. Over time, typically you're going to be writing custom stored procedures. You're going to be using non-standard SQL extensions. It's going to get harder and harder over time if you do want to switch out implementations. It means that you're signing up for vertical scaling. And the different database vendors have done a good job over the years at getting better and better at vertical scaling. But of course, horizontal scaling is typically going to win as you continue to grow. And it means that you have a single point of failure. It means that that single database, if it goes out or if it has problems, could affect lots of people. So we're going to say this is an anti-pattern in the microservices world. And so moving to microservices means that we're going to decentralize these data stores. We're not going to let services share data stores. And developers love this, right? Because we get to pick the data storage technology that makes sense for our service. That's typically going to be based on our data access pattern. So we're going to think about how we need to read the data, and we're going to use the right data store for the job. Often that's more than one data store. Often that's multiple data stores. And the nice thing about being in AWS is you can pick 2, 3, 4 data stores, whatever you need for the job. It's very easy to do. It means that you can move very fast, right? Because you don't need to depend on anybody for a schema change. Your team can agree on it, you can push it out, and you're done. It means that you're going to scale independently, so that's important for cost. And it means that you can really have full control over how you're scaling your data tier. And again, we want to gate that data through the service API. We don't want to share the actual raw connection to our data store with any of the other services because they're immediately going to start depending on that implementation. Another challenge that we hear about is transactional integrity. Right? So typically with a giant monolithic database, you can use the transaction features that are built into your database engine, and you can make sure that you have whatever transactional guarantees that you need. And if you split that data out into multiple services, and you now need to pull bits of data from different services, well, how do I do a transaction? So there's two ways to think about this. The traditional model with databases is the pessimistic model. It means you're going to design for the 1% of the cases where you have a transactional issue, and you're going to do a lot of work ahead of time to make sure that you're ready for it. And you can stick along with that model. You can move that transaction into your client application logic. You can own it yourself, and you can say, I'm going to go hit these services, and if there's a problem, I'm going to write logic that's going to solve it. You can create a new microservice and call it the transaction manager or the distributed locking service. And you can have lots of distributed locks, and you can go get a distributed lock, do the work that you need to do, and then release it back. There's some frameworks out there. DynamoDB, for example, has been used for this. And then another option is to simply rethink your design. And so many times, strict transactional integrity is actually not needed. And so every service team can think about whether or not they need strong transactional guarantees. And in many cases, it's actually not necessary. So you can switch to an optimistic model where you're programming for the 95%, the 99%. You can accept that eventual consistency is fine for your use case. Eventual consistency is great from a scaling perspective. If the operation is idempotent, if you're doing a put operation across multiple services and you can put it more than once and it's not going to affect the state of the system, if you have some kind of transactional issue, you can just do it again. You can fix it later, so you can think about having a dead letter queue or some kind of place where you're keeping track of issues that happen during the day, and you can go back and fix them later on. So for some use cases, it's not really urgent to fix these kinds of issues, and you can focus on that 99% optimistic case. Or in some cases, you can actually say it doesn't matter. So another challenge with this model where we're splitting out data into different services is aggregation. So great, we've split this data out into lots of small data stores. Well, now I need a roll-up at the end of the day. Right? Somebody in the business is asking me to have an aggregate view of what the services have inside them. And so there's three ways that you can think about doing this. The first model is probably the most pure. It's a pull model where you create, as part of your API, a way to get batch data out of it. And so you can have a marker, and you can have batch get API calls, and your clients can go and pull all the data out that they need and then go aggregate it somewhere. That's probably not going to be very efficient. And so in practice, what we see is typically more of a push model. So your services are all going to agree, in this case, to be tightly coupled to something like S3 or CloudWatch or maybe an aggregation service that you write, and you're going to push that data every minute, every 5 minutes, every so often to this centralized place that it can get rolled up. We just announced a service, Kinesis Firehose, which could potentially be great for this, where you drop the Kinesis agent onto the hosts that are generating this data, if it's log data, for example, and it'll automatically get pushed out to S3 or out to Redshift. So that could be a good option. And then PubSub is another option. You can create a subscribe API, call a method into your API, and you can let the other services that need to do this aggregation subscribe to a feed. You can push that data out using Kinesis or SQS or some other method so that the different services that need to do aggregation can get exactly the data that they need. It's a little bit more sophisticated. That'll give you some more fine-grained control. So moving on to deployment. So continuous delivery and continuous deployment work great with the microservices model, and we see Gilt do this, for example. So the right build pipeline for each service is really going to be up to the service team. So some service teams are going to say, hey, we want to do continuous delivery all the way to some staging environment, for example. So we're going to get it into staging, we're going to run some integration tests, and then we're going to have a manual push to production. And for some services, that's the right call. It's too critical to do automated deployment. For other services, customers tell us, hey, it really doesn't matter. If we push we push a bug out into production for this service, not a big deal. We can always roll it back later. We can detect it. And so it's really up to each team to make that decision. How far do we want to push automation? There's lots of great software out there for this, and so you can pick the one that you're currently comfortable with, or you can try something new. Of course, Code Pipeline gives you the ability to visually draw this out, and so that's another thing that you can think about looking to do. So another issue, and this is something that Gilt ran into, is running multiple services per container or per instance, depending on the deployment methodology that you're using. There's some issues with doing this. This is what we're used to in the monolithic world. But it means that monitoring is now going to be shared across different service teams. So if I see an issue with high CPU, high memory, operating system errors, it's not easy to pinpoint what the culprit is. It means that my unit of scale is tied to multiple services. So my user service in this example needs to grow. My other services are going to get dragged along with it. That's not cost efficient. It means there's a lack of clear ownership. Which of the service teams owns this instance? And it means that immutable deployments are going to become very hard because each instance or each container has multiple folks inside of it that may be wanting to make changes. So we're going to say, again, this is an anti-pattern for microservices architecture. So there's a lot of benefits by thinking about going to a single service per container or a single service per instance. A lot of these challenges go away. And so this is definitely a good pattern to follow with microservices. And of course, there's a third option, and we're seeing more and more of this, which is to get rid of the services altogether. Plenty of immutability there, plenty of scaling there. API Gateway can handle the front end of this. Lambda can handle the execution, and then you can pick your favorite backend for the data store and just get out of the business of doing these deployments at all, and just push code. So definitely an emergent pattern and a great fit for microservices. So the next issue that we see is I/O explosion for the purposes of this talk. And what that means is, as you get many dozens or maybe many hundreds of services running out in production, your dependency graph is going to get harder and harder to understand, or maybe even compute, or maybe even print on a reasonably sized piece of paper. And so that's fine, but it means that some of your services may wind up running very hot. Right? They're just very popular. They're in the critical path for a lot of other services. And that's going to become expensive. You're going to have to scale those services out to handle the increased CPU network traffic. And so we can see in this diagram, a single request can fan out into potentially many, many requests. And so as a good citizen in this ecosystem, we can think about it as a service consumer adding a local cache. And we can actually pull whole branches of this diagram and make them not necessary. So by doing that as early as we can in the call chain, that means we'll be able to make the most savings. Another challenge that we've seen is hotspots, and again, that just means you've built one of the services that's very popular, and that's a nice thing. But how can we sort of reduce the number of calls here? But in this case, we've got this user service. It's being asked the same question repeatedly. There's really no reason for that to be done. And so you can borrow a term from software development world, which is a dependency injection, which means the service is going to require that you pass along some of the data that it needs as part of its API. So you can't make the service call without going off to this user service and getting the data that the shipping service needs. In that case, we're actually going to force, by the API design, a good behavior here, and we're going to take some of the pressure off of this user service. So another thing to think about from the service provider side, where it makes sense. So next, I'd like to talk a little bit about monitoring. And so monitoring can also become a challenge in a world where we've got lots and lots of services. And so it's important to think about splitting the monitoring horizon into two. There are metrics, and so latency, request per second, error rate, that your clients of your service care about. And so again, it's important to make sure you're publishing those and making those available so people can understand the health of your service. And then there's all the other metrics that have to do with how you've built this thing. And frankly, nobody else cares how you've built your service, right? That's up to you to understand. It's up to you to change if you need to. But when you have an issue with your service, you're going to care very much about the details. And so we can give the internally relevant metrics over to the service teams. They can pick their favorite monitoring framework, and again, there's lots out there. And they can use the ones that are the best suited for their application. So another challenge is logging. Again, we want to keep the data stores separate. We want to keep the API boundary in between these different services pure. But logging is another case, one of these edge cases where you really want to agree on a logging solution across the board. By doing that, you can push your logs from all of your service into a common logging service like Sumo Logic, for example, or Splunk. You can build your own ELK, Elasticsearch, Logstash Kibana cluster if you like. Whatever the solution is, pick one and stick with it, and then you'll be able to correlate. So correlating requests becomes increasingly important when you have lots and lots of services. Where did I have a failure somewhere down the line here? And so if you take the time to establish this logging standard across all of your teams, you can use correlation IDs, and this becomes very important. And that could be as simple as just at the very beginning of your call chain, pick a unique identifier, and then stick that in the header of every single API call. And the modern logging aggregation tools are great at having you type in a string into the search box and seeing a time-ordered set of every single log entry from every single service. So that's a great way to do some troubleshooting. And it's easy to set up. And so we're just about up on time here, but we talked about 6, again, not an exhaustive list, but 6 things to think about as you begin this journey towards a microservices architecture. So there's some great related sessions here that I would encourage you to check out. Please complete your evaluations, and we're right about out of time, so thank you very much for attending.